Hello dear friends, welcome to my channels. Today's discussions is introductions to topological fluid dynamics. These lectures will follow the kind of new revolutions that we are living these days due to the great achievements and the successes of recent approach of topological theory to physical sciences. This has had a great impact in string theory through the work of Edward Witten and others. This approach, actually much older, is an approach rooted in the work of Kelvin 1868 when he wanted to produce a theory of everything until a theory of matter, exactly as we would call it now a theory of fundamental physics. He conceived this idea that vortices were like infinitesimally small particles. We could perhaps paraphrase that saying that is like a string in fluid medium is like fundamental energy field of invisible scale, and the idea is extraordinary idea. 1816s, he had the idea that a vortex ring could link or not in space, and because of the permanence of ideal fluid, no dissipations, then topology had to conserve first thing and second thing. If topology is conserved, suppose you have a knot and you have a different type of knot of different complexity, then the two knots had to have a discrete amount of different energy. So through this idea, he envisaged the possibility to interpret discretization of energy through topology. This is a incredible idea 1860, because he not only understood that through that thinking was possible to determine a spectrum of fundamental energy states. It could also envisage the possibility that these states were independent from the metric. So many ideas already there that we now attribute maybe to more than scientists. This theory did not survive in the 18. He had a number of outstanding followers, including J.J. Thomson. J.J. Thomson was a brilliant mathematician in Trinity, and he worked on mathematical aspects of this vortex atom theory. 20 years later, 1818, the more things come uneasy, and finally he dropped the theory to become a physicist, and in 1906 he got Nobel Prize in physics for discovery of the electron. His first work were on the mathematical foundation of the vortex atom theory, So this is very briefly the story about the topological fluid mechanics that has gone shadowed, has gone down after that period because of the great successes of physics and the other interests in fluid mechanics are now takes etc, but we inherit from that time this approach, the approach that through field the theory as we can investigate fundamental aspects, if not of the fundamental nature but at least of nature. Now I am going to present the introductions to this field that is now very rich. This in last 20 years we saw a very exciting new discovering covering coming from very talented young mathematician and physicists, and so this field that survived through periods of ups and downs is now resurrecting and has having great impetus. Now I will draw your attention to a number of facts that are also relevant for mathematical problems and aspect. Let me just draw a few pictures. I can't draw things very nicely. Sometimes we have something like this and this get linked with this part and it goes back like this. Suppose you have something like this and imagine that this is made some material, plastiline plastiline, and you can deform it and you want to play with the material you want to play with this material by deformation and continuous deformation, and you want to reduce this material to this material to this material. I just reduces. Definitions of this material, imagine is plastiline. You can deform this to this. You can deform this to this to this to this to this. It defies our imagination. We believe it is not possible, but it is possible. You can deform continuous without cuts this structure to the structure. One way to do it is deform this to make it a very thick, and then we can use this to enlarge. This way I can write this is the enlarged, this is, and this portion and other portion is just cut this way, and after that it can become this way, and after that some process we can get easily this diagram. The other and reduce this, and there is another situation, continuous deformation. There is another situation where we may start with fluid, we may put some light fluid on top. So suppose this is light fluid, that stays on a heavier fluid. If we reverse the situation, this is stable, right? Because gravity is a pull of gravity working downwards, and imagine now that this part of the fluid is made by a heavier fluid, and for some simple reason, for simplicity, we assume that a certain point this collapses. We know this oil and water or vinegar and oil etc etc, we know that the two liquids oil and vinegar are hardly miscible. If we want to mix them, we have to stir them up a lot, to put a lot of energy. Suppose that this fluid is heavier but not so much, so that after some time, as time passes, the fluid collapses here, and at a certain point floats on in the bulk of the other fluid, of the lighter fluid. Then there is a stress, and then this strain, as time goes to infinity and appears. Suppose the fluid is heavy enough to be balanced by gravity at this stage, then again if you look at the situation at the beginning and at the end of where the fluid, where that goes down like this, as time passes, then you have change of topology of this ambient space without cut. How is possible? Is a continuous deformation. There is another famous example, and this is quite recent and has been done experimentally. And this, you imagine to drop something, a drop, and this drop goes into the water, and then there is a reaction, and that you get a reaction from the water. So this is water, and there is a cusp for m, and by changing is air, and air may be some particular liquid, is not entirely water. You may put some glycerin, you may change some particular physical properties of this, but you can get a cusp. This cusp in the infinitely thin, here with a extremely thin radius of curvature. This problem share a one aspect is what in mathematics is called a singularity and singularities. They share also the problem that in this case there is no change of topology. Here there is no change of topology under certain assumption, and here there is no change of topology except that there is a class, but there is a edge of a point in space where the radius of curvature can be extremely small. How small? Or very small, tends to minus something thing meters, so small that we go to scales of quantum physics, so that classical analysis gives you the wrong answer, because you get to a limit where you get wrong numbers for quantum aspects. You go below certain scales that are absurd. Now all this problem share common features: continuous change of shape without cuts, and emergency of singularities in finite time. Maybe so these aspects are central to modern research in mathematics, and indeed the problem of large transformations in finite time under equation of fluid dynamics is a well-known Clay problem of the Clay Institutes. Clay problem of the Clay Institutes is one of the 8, and solve the problems of 7, and solve problems of the millennium. It's a $1 million prize for this. So this is just to give you an idea that these are challenge, challenges, and represent all these phenomenon challenges for mathematics. So let's introduce some tools. First of all, I will focus on to keep things simple on ideal fluid dynamics. Ideal ideal context. Ideal is of course an idealization of the real world, but we may capture phenomena that to a certain approximation are relevant for finer aspect. So I will assume a continuum hypothesis. Everything is continuous till a very small scale. How small? Any scale, we like any scale. So to know the problem of viscosity, if you go and below a certain scale, then can we define viscosity? This is the first assumption continuity associated with that. Briefly, what I wanted to stress is that we will focus on certain flow maps. So I will consider the motion of a fluid to say from a point x0 to a point x, and x0 is the initial position, x will be at certain time. The initial positions x will be at a certain time, and this is a flow map that transformed a structure, a vortex of magnetic field. Some brings a point in the fluid to the new position. Now this flow maps I constrain myself to work in a set of flow maps that are like this. I take these flow maps to be continuous smooth with the new large enough so that we have a inverse map by minus, and that gives me access 0 through the investment and the t if we have t, and this is for capital T finite in a finite interval to new number. We can always go back to x0, right? We had this problem of the custom. Remember, each point when the surface produced viscous, each point of water goes up, and at certain point we should be able from this 5 minus 1 to distinguish here every single point that collapses to one point, which contradicts what can reverse this experiment with the usual experiment. Tap water, you shut up that the flow of water, and at a certain point from water forms a drop. There is water here. At the certain point of the drop start to detaches from the fluid. What happens to this point? This break down. We have no longer inverse mapping well defined. We have problem with the inverse map. So as we define our fluid to be continuous with illness that exists at all time, we immediately cut out many important problems main important problems of real life, but also mathematically we may have problems for a singularity for the inverse of the flow map that is ill-defined or even worse in some natural circumstances. We have instead of a cusp, we have an angle, and the angle is to some extent is the some problem where the tangent at the angular point is. We have a problem there too. It depends on the context exactly set of flow maps, and by doing this we cut out many problems we don't know how to handle. Let me go back to the point. Suppose we have two field lines. That intersect exactly. What is the physics there? What is the mathematics? There can we talk about the tangent at a point. There this is normal problem tackled by many contexts of physics is called reconnection. The state of a field line that goes through the other are the instant of the intersections. There is a difficulty tackle the problem because we don't have the mathematics. So emphasize size here is that we are using old style mathematics, but we used also to think at the same time of something new in mathematics to have new techniques to handle these problems singularities that are associated with changes of topology. I mentioned in the first diagram, I told there is a no changes of topology is continuous deformation at all time. Here, this is the first diagram. I mentioned the deformations at all time. No changes of topology continuous. What is the singular? It depends on the context. Losing the inverse is key point of singularities. So friends, you see this inverse. If it is the losing the inverse, it is the key point of singularities. If your morphism is a continuous deformation that is differentiable at all times, so deferred morphisms may not have the inverse map. All right, so this is just a little preamble. We are going to use some tools. DDT tends to total derivative of quantity. Suppose that I take a velocity u, and u is function of space and time. Functions of space and time. Now the accelerations E is equal to du divided by dt. It can be represented as del u by del t plus u into del u. This way, this portion is called contributions in term time. This portion is contributions in term times. This portion is contribution in term space. So A can be written. Now friends, we are discussed these equations du by dt del u by del t plus u into del u. So friends, whatever you see, this portion is called temporal derivatives. This is temporal derivative, and this portion is called convective transport derivative, and d by dt is total derivatives, and del u by del t is equal to linear part and non-linear part. The notion of field line, so I will stick to u, and u is the velocity field. Streamline line in RQ. At each point, u is defined to be identified with the unit tangent. So if we prescribe the unit tangent at each point of this line, say this line, we have the unit tangent t. Unit tangent t hat is equal to t1, t2 and t3, and velocity also 3 component of the velocity. U is equal to u, v and w. Streamline definition is velocity line is simply given by u over, if you like, dx u equal dy over v. This is equals to dz over w. So dx over u equals to dy over v, and dz equals to dz over w. X is given by x, y, comma z. This is the definitions of x, and x is the functions of x, comma small x, comma z, small y, comma z. Definition of streamline. Notice that we may divided everything by ds. So whatever we get, dx divided by ds divided by u, and dy divided by ds divided by v, and dz divided by ds divided by w. Velocity u with the unit tangent t. So u proportional to t, tangent t. This is a vector field line. I define a magnetic field, the same thing have a magnetic field that is identified with the unit tangent on curve C in space. Field lines will be very important for us. We will talk about the collection of field lines, and I would like to introduce a kinematic results due to Reynolds. So this is a kinematic transport theorem. Reynolds transport theorem states that the rate of change of extensive property n for the system is equal to the rate of change of n within control volume. The net rate of flux of the property n through the control surface. In differential calculus, the Reynolds transport theorem, simply Reynolds theorem, named after Osborne Reynolds' three-dimensional generalizations of the Leibniz integral rule. It is used to recast time derivatives of integrated quantities and is useful in formulating the basic equation of continuum mechanics. So friends, general form is dn by system substantive derivatives. Reynolds transport theorem refers to extensive property n of the fluid in particular control volume. So friends, general form is dn system divided by dt is equal to integration of control volume del by del t is equal to rho eta dv into the integration of control system, control surface. Integration cv refers to control volume and cs refers to control surface. Control surface rho eta vb eta dA. Here vb is the velocity of the boundary of the control volume, boundary of the control volume, into eta into dA plus control volume, control surface plus integration of control surface rho eta vr eta dA, where vr is the velocity of the fluid with respect to the control surface and n is the outward pointing normal vector on the control surface and a is the area. So friends, thanks for watching. I will create more video based on topological fluid mechanics. This is just introductions. I hope I can clear this concept, friends. Thanks for watching.